In this episode, we're going to build a mental model for how shell scripts decide whether something worked, how they pass information from one step to the next, and why tiny mistakes in that flow can turn a clean script into a confusing mess. A lot of beginners assume scripts fail only when something crashes loudly, but in Linux the more common failure is quiet. A command prints nothing, creates no output, and still looks like it ran, but it actually signaled an error through a return code. At the same time, scripts depend on arguments to know what to act on, and those arguments arrive as positional parameters that can shift around in ways that are easy to misunderstand. If you learn to read return codes and handle arguments intentionally, you can make scripts that explain themselves when they fail, instead of forcing you to guess. That skill is less about memorizing tricks and more about learning the language a script uses to communicate success, failure, and intent. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A return code is a small numeric signal that a program gives back to the shell when it finishes, and the shell uses that number as a quick summary of how the program ended. The most important convention is that a return code of 0 means success, and a non-zero return code means something went wrong. That can feel backwards at first because we often think of 0 as nothing, but in this world 0 is the value that means no error happened. The non-zero values do not have one universal meaning across all commands, because each program can define what its codes represent, but the success versus failure split is consistent enough to be reliable. This makes return codes a kind of universal handshake between programs and scripts, allowing a script to make decisions without having to parse human-readable text. When you start thinking in return codes, you stop relying on whether output looks correct and start relying on whether the step actually reported success. The shell keeps the most recent command's return code in a special parameter called $, written as $. It is not a normal variable you set yourself, and it updates automatically every time a command finishes. That also means it is fragile in a very specific way. If you run another command, even a harmless $1, changes to the new command's return code and the previous one is gone. Beginners often check too late and accidentally read the status of a different command than the one they cared about. The right mental habit is to treat as a snapshot you either capture immediately or you use immediately, because it is always about the last thing that ran. If you ever feel like a script is lying about whether something worked, one of the first suspects is that was checked after another step already replaced it. It also helps to understand that scripts and commands can be combined in ways that make return codes more or less obvious. When you run one command, the return code is about that one command. When you run a pipeline of commands where output flows from one to another, the shell still needs to decide what return code the pipeline should have as a whole. Different shells and different settings can influence whether the return code reflects the last command in the pipeline or whether the pipeline is treated as failed if any component fails. You do not need to memorize every rule to be safe. You just need the mindset that complex command chains can hide failures if you only look at visible output. For beginners, the important takeaway is that return codes are the official signal, and you should design your script so it checks and reacts to them at the moments that matter. A script that never checks return codes is like a pilot who never looks at instrument warnings. Now let's connect return codes to arguments, because error handling often starts with making sure you even have valid inputs. When you run a script, any extra words you provide after the script name become positional parameters. Inside the script, the first argument is $1, the second is $2, and so on. These are not the same as normal variables either, because they represent the arguments the script was called with, and they reflect the order the caller used. There is also a parameter called $0, which is typically the script name itself, and that can be useful when your script prints a message explaining how to use it. The key beginner idea is that scripts do not magically know what you meant. They only know what arguments they received, in that order. If you pass too few, too many, or values in the wrong positions, your script might still run but behave incorrectly. So argument validation is a form of error handling before you even get to return codes. Two very important positional-related parameters are $#, which tells you how many arguments were provided, and $at, which represents all the arguments as a group. For beginners, the difference between treating all arguments as one big string versus treating them as separate items is where a lot of confusion lives. The script often needs to loop over each argument, treat each one as its own piece of data, and preserve boundaries correctly so the script does not accidentally merge or split values. That is why scripts commonly check $hashtag at the beginning to ensure the caller provided the right number of inputs. When you combine that argument count check with clear messages, you create a script that fails early and politely instead of failing later in strange ways. That early validation reduces the number of possible causes when something goes wrong, which makes troubleshooting much less frustrating. When arguments are used inside functions, the same positional concept appears again, because functions also receive positional parameters. Inside a function, $1 refers to the first argument to that function, not the first argument to the whole script, and that difference can surprise new learners. This is one of the reasons functions can improve error handling, because they let you validate inputs at the function boundary. A function can check how many arguments it received, confirm that they look reasonable, and then either proceed or signal an error by returning a non-zero status. That return status becomes the function's return code, which the caller can check just like it checks a command's return code. You should think of this as building your own little commands out of functions, complete with success and failure signaling. Once you adopt that pattern, scripts become collections of small, testable units rather than one long chain where failures are hard to pinpoint. A classic error handling pattern is to run a step and immediately test whether it succeeded, and then take action if it did not. The action might be printing an explanation, cleaning up a temporary resource, or stopping the script so it does not continue in a broken state. The reason this pattern is so common is that continuing after a failure often causes data damage or misleading output. If a script expects a file to exist, but the step that created it failed, every later step is now operating in a world that does not match the script's assumptions. A beginner sometimes tries to be resilient by ignoring errors, but that usually creates a more confusing failure later. The more disciplined approach is to decide which errors are recoverable and which ones should stop the script immediately, and then implement that decision consistently. That consistency is what turns error handling from a collection of hacks into an intentional design. Another useful pattern is the idea of a guardrail check at the start of a script, where you verify prerequisites before doing anything expensive or risky. This includes verifying argument count, verifying that required input files exist, verifying that a directory is writable, or verifying that the environment is what you expect. The point is not to be paranoid. It is to make failure messages meaningful. If the script fails 3 minutes in because of a missing file, that is a bad user experience and a debugging headache. If it fails in the first few seconds with a clear explanation of what is missing, the fix becomes obvious. Guardrails also help you avoid partial work, where the script creates half an output and then fails, leaving a messy state behind. Even for simple scripts, guardrails are often the difference between something that feels professional and something that feels fragile. It is also worth addressing a subtle but important mindset. Return codes are not moral judgments. They are information. Some commands return non-zero status for situations that are not catastrophic, such as when a search finds no matches. To a beginner, that looks like an error, but to the program it might simply mean the condition was false, like a query returned 0 results. This is why you should avoid treating all non-zero returns as identical, especially when your script logic depends on certain conditions being true or false. A good script author learns which steps are expected to sometimes return non-zero and handles those cases intentionally, perhaps by branching logic rather than exiting. You do not need to memorize every command's behavior, but you should develop the habit of checking what a return code means for the program you are using and designing your handling around that meaning. This makes your script's behavior predictable and reduces false alarms. Error handling patterns also include the way you communicate failures to the outside world. When a script fails, it should signal failure through its own return code, not just by printing text. That matters because scripts are often used inside other scripts, automation tools, or scheduled jobs, and those systems often rely on return codes to decide whether to continue or alert someone. If your script prints a scary message but exits with success, the outside system may think everything is fine. Conversely, if your script exits with failure without explaining why, the operator is left guessing. The best practice is to do both. Print a clear, concise explanation of what went wrong, and then exit with a non-zero return code that signals failure. This is another place where functions shine, because you can centralize the logic for reporting errors and returning failure codes, rather than repeating similar text throughout your script. A frequent beginner mistake with positional parameters is accidentally shifting them in your head without realizing the script sees them exactly as passed. For example, if you add a new optional argument to a script later, every position after it may change, and older calls to the script may now map values to the wrong positions. This is why careful scripts either keep a stable argument order or validate and document how arguments are interpreted. Even when you are not writing documentation, you can design your script so the usage message that appears on error explains the expected arguments in a human-friendly way. The practical skill here is recognizing that argument handling is part of the interface of your script, like a button layout in a user interface. If you change the interface without safeguards, you will create failures that look like logic bugs but are really input mapping problems. The safest beginner pattern is to treat arguments as precious inputs, validate them early, preserve them carefully, and treat return codes as your script's truth signal. When a step fails, decide immediately whether you can recover or whether you should stop, and make that decision consistent across the script. When you write functions, treat them as mini programs. They accept inputs, they validate, they do their work, and they return a status that the caller respects. When you check $, or a function's return status, do it right away, and do not let unrelated commands overwrite the value you meant to examine. Over time, this approach builds scripts that fail loudly when they should, continue safely when they can, and communicate their state in a way that other tools can understand. That is the difference between a script that sometimes works and a script you can trust. By the end of all this, the big lesson is that Linux scripting is a conversation between steps, and return codes and positional parameters are the language that conversation uses. Positional parameters tell your script what the caller intended, and return codes tell your script whether each step actually succeeded. Error handling patterns are simply the habits you adopt to keep that conversation honest, clear, and safe, especially when unexpected situations happen. When your scripts validate inputs, check status immediately, and stop or branch thoughtfully, you prevent tiny mistakes from cascading into confusing outcomes. That confidence is exactly what you want as you prepare for Linux Plus style thinking, because it means you can read a script and predict how it will behave even before you run it.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.